arrives, the kernel pushes a SIG frame onto the kernel stack of the interrupted process. The SIG frame is a meticulously designed data structure that holds all the necessary CPU context. It includes general-purpose registers, the instruction pointer, stack pointer, and processor flags, essentially a complete snapshot of the CPU state at the moment of interruption. This precise capture is vital because it allows the kernel to completely restore the process's execution environment later. Without this, returning from a signal handler would be like trying to resume a movie from a random point without knowing where you paused. The SIG frame ensures a seamless return. With the context saved, the kernel then shifts its focus to preparing the user space environment for the signal handler. Once the kernel has saved the process's context, it needs to carefully orchestrate the switch to the signal handler. The kernel doesn't just call your signal handler directly. Instead, it performs a clever trick. It manipulates the user space stack of the target process. The kernel pushes a new stack frame onto the user stack, which includes the arguments for the signal handler and, crucially, the address of the SIG return system call, which we discussed earlier. The instruction pointer, RIP, of the process is then set to point to a special trampoline code in user space, which then jumps to your actual signal handler. This trampoline ensures that when your handler finishes, it will call SIG return to properly clean up and restore the original context. It's a carefully choreographed dance to ensure a smooth transition from kernel space back to user space for signal handling. Finally, let's see how SIG return brings everything back to normal, ensuring the signal handling is transparent to your application. After your signal handler has done its job, how does your process seamlessly resume exactly where it left off? This is where the SIG return system call comes into play. When your signal handler completes, it doesn't just return like a normal function. Instead, the trampoline code we discussed earlier invokes the SIG return system call. SIG return's job is to read the saved context from the SIG frame that was previously pushed onto the kernel stack. It then restores all the CPU registers, the instruction pointer, and the stack pointer to their original values. This restoration is what makes signal handling largely transparent to the interrupted application. Your process continues as if it was never interrupted, ensuring robust and resilient system behavior. Understanding these low-level mechanisms helps you appreciate the complexity and robustness built into modern operating systems, allowing for powerful and responsive applications.